Okay, this week we're going to learn about pressure, what it is, and what it means for weather. So, with that, let's see if we can move along here a minute. And what is pressure? Well, air exerts a force on any object. All molecules move, first off. And when they move and hit other molecules, there's a force exerted. So, the more molecules, the faster they're moving, the more force there is. And air is basically pressure is what comes out of this. The total air pressure is the accumulation of all these forces. So air has weight or pressure, and each gas has a different pressure. So if I told you the pressure was 5 inches of mercury for one gas, 6 inches of mercury for another, you would add up the pressures of each one of those different gases to get the total pressure or the total air pressure for the atmosphere. So, and air pressure depends both on the motion of the molecules and the number of molecules. So, everything has air pressure. It's mass times acceleration. And it's due to gravity is the weight part. Well, think about it. Gravity pulls everything down, so all that air that's above you has weight. Guess what? You have air in you that's pushing back against it, so you're not going to collapse. That's why structures don't collapse. But we can look at a barometer and see that the pressure generally be pushed up in a vacuum tube of mercury, about 14 inches or so up or more, sometimes 30 inches of mercury. 29.992 inches of mercury is actually the normal air pressure that you would expect to see at sea level. So that's one way of looking at it. Now, they're all different units of pressure. You're going to see a lot in this course about millibars. Millibar is more of a metric unit, but it makes the math tremendously easier. And because of that, most of the pressure you're going to see on weather maps is going to be recorded in millibars. However, if you're listening on TV, you're probably going to hear it in inches of mercury, just because most people are used to hearing inches. They're used to thinking in the English units. So, an interesting thing. Air is considered a fluid, but it's a compressible fluid. So, in other words, you can push air together into a tighter and tighter space. Try doing that with water and you'll see it gush out over everything. But air can be compressed. So, with that in mind, there's a drop in pressure with altitude is greater in the lower troposphere. In other words, the air is being pushed down tighter and tighter together. So pressure will drop very quickly at first and then slow down the further up you get. And they're vertical profiles. We've done averages of the atmospheric pressure and temperature called standard atmosphere, and we have it by different seasons. So there's a horizontal variation in air pressure. It's pretty daggone small relative to the vertical variation in air pressure. If you were to look at the horizontal changes in air pressure, just see it from here, you see basically 1020 at the end almost, maybe 1019. At the lowest point, 1008. That's a whopping 11 millibar pressure change. If you were to go into vertical and have that kind of pressure change, all right, 850 millibars. You figure 1,000 millibars is the surface. 850 millibars is 5,000 feet up. So you lost 150 millibars in 5,000 feet. Not even a mile. So the pressure change is much faster in the vertical than it is in the horizontal. Another interesting thing is we learned with temperatures that it means they're based on the kinetic energy of a molecule. So the more they move, the higher the temperature. Well, air is not a closed container. Air can go anywhere. So with that, if the molecules are moving very fast, they're hitting each other, they're pushing each other further and further apart. So there's less molecules and typically less weight. So the warmer the air is, the less dense the air is, probably the lighter the air is. Now, when it's very cold outside, the cold air is more dense, has less kinetic energy, molecules are closer together, so that as you rise up, pressure is going to drop fairly quickly. However, during the summertime, the pressure is going to drop slower. So the more humid and hot the atmosphere is, the slower the pressure is going to drop into vertical. And the more colder the atmosphere is, the faster the pressure is going to drop into vertical. So let's just take a quick peek at that a minute. I wanted to show this because here is today's weather map. We have fairly strong low pressure over here north of Montana. About 990 millibars, something in that neighborhood. And here is an actual weather map in that neighborhood, and here 995, 994. So, but look at how slowly it changes going this direction. 994, all the way to 997, 1003. That's only 6 millibars. And I probably traveled 500 miles. So the pressure is not changing greatly in the horizontal. That's the main point I'm trying to emphasize here. Yes, the pressure does lower with low pressure and bad weather. And you can see there's a lot of bad weather here with this low. But it's taking its time. Now, if you looked at the vertical, you would see there's actually a trough back here of lower pressure. Colder air was to the west of that low, so that the cold air is causing the pressure to drop faster. And guess what? You wind up with a trough of low pressure, or actually low pressure, a loft. So what we've just learned, you can apply here in real life. So moving on to the next slide, we have winds that converge and diverge. Converging winds are winds that are coming together. So when they blow towards each other, the wind is going to push molecules together. And what happens is the air is going to try to either go up or down. It's not going to want to go in the same spot, even though they're going to tighten. It's going to try to push up or down, either into the ground, maybe, or if it's up above, it's going to come downwards. So converging air, depending on where it's occurring in the atmosphere, if it's occurring aloft, it pushes air towards the ground. If it's occurring at the surface, it pushes air up. Divergence, just the opposite, and has just the opposite effect. If it's aloft, it's pulling air apart, so the air from below is going to want to come up. If it's happened at the surface, air from the top is going to want to come down. The ideal gas law basically is made up of relationship between temperature, pressure, and density. They are directly proportional. So once I know one or two, I can know the other. So it's a very nice way of estimating temperature or estimating pressure if I know the other ones. Think about expansion or cooling. The air is being pushed apart. Well, if you rise in the atmosphere, there's less and less air, right? So the air is actually being pushed apart. That's why the air is cooler when you go up. You come down in the atmosphere as you're sinking, the air is pushed tighter together. That's why it warms up as you go lower in the atmosphere. So air currents that ascend are going to cool. Air currents that fall, come downdrafts, are going to warm. And here you can actually see the mechanisms, how they work. Interestingly, if an air parcel is rising up, air parcels, we're going to talk about air parcels a lot. Air parcels are just a bunch of air. Maybe it's 10 feet by 10 feet across. Maybe it's a mile across. Maybe it's more. Maybe a mile high. That bunch of air, as it's rising up, is going to be expanding and cooling. If it has no moisture in it, it's going to cool at 9.8 degrees Celsius per 1,000 meters. So if you knew that your air was dry and you were climbing a mountain, you can tell you every 1,000 feet, temperature is going to drop 5.5 degrees Fahrenheit. So maybe if I go up 10,000 feet, I just dropped 50-some degrees. That's pretty cool. Now, we did learn last week that on temperature there's latent heat. And when moisture condenses, water vapor condenses into a droplet, it releases latent heat. With that, it means the air parcel is not going to cool as fast. So when clouds are forming, the air parcels that's forming those clouds are only cooling at 6 degrees Celsius per 1,000 meters instead of 9.8. So the air parcel is actually staying a little bit warmer. So with that, that is really what I have to say about pressure today. So if you have any questions, and you're going to hear a little bit about it this week, you're going to talk about whether low pressure systems are passing your area or not. And there are going to be some weak lows passing your area. See if they impact the weather, or whether high pressure makes you have wonderful clear skies all week. So hope you got a little bit out of this, and let me know if you have any questions.